Ever wondered how the flow of electricity in a circuit works? How do currents and voltages behave in a circuit? The answer is in Kirchhoff's laws. Kirchhoff's laws are the fundamental principles that govern the behavior of currents and voltages in electrical circuits. Named after Gustav Kirchhoff, a German physicist who formulated these laws in the mid-19th century, these laws are the cornerstone of circuit analysis. The first one, Kirchhoff's current law, often abbreviated as KCL, states that the total current entering a junction in a circuit is equal to the total current leaving the junction. Imagine it like a traffic system for electrons. They can't just vanish or materialize out of thin air. Every electron entering a junction has to leave it, ensuring a balance of current. The second law is Kirchhoff's voltage law, or KVL. This one deals with the concept of loops in a circuit. KVL asserts that the sum of the electromotive forces and the products of current and resistance in any closed loop of a circuit equals the sum of the potential drops in that loop. In other words, the energy and voltage that travel around a circuit loop must make a round trip, maintaining a balance of voltage. These two laws may seem simple, but they have profound implications. They help us understand the flow of electricity in circuits, allowing us to predict the behavior of complex electrical systems. Whether you're designing a new electronic gadget, troubleshooting an electrical problem, or just curious about how electronics work, you'll find that Kirchhoff's laws are invaluable tools. So, let's get ready to dive into the fascinating world of circuit analysis. With Kirchhoff's laws as our guide, we'll unravel the mysteries of electrical circuits, one loop and junction at a time. Now that you've been introduced to Kirchhoff's laws, let's delve into the details. First up, let's look at Kirchhoff's current law, or KCL for short. This law is all about junctions in a circuit. You know, those points where wires meet and electrons decide which path to take. It's like a crossroad, but for electrons. Now, imagine you're overseeing traffic at a busy intersection. Cars come from all sides, but the number of cars that enter the intersection must equal the number of cars that leave it, right? Well, KCL is based on a similar principle. It states that the total current, or the total number of electron cars, if you will, entering a junction equals the total current leaving it. This might seem obvious, but it's a fundamental principle that governs how electricity behaves. So, let's say we have three wires meeting at a junction. If the currents in these wires are I1, I2, and I3, then according to KCL, the sum of I1, I2, and I3 must be 0. This means that if I1 and I2 are entering the junction and I3 is leaving, then I1 plus I2 must equal I3. This law is based on the principle of charge conservation, which states that electric charge can neither be created nor destroyed. So the amount of charge entering a junction must equal the amount of charge leaving it. In other words, the electrons, those little particles carrying charge, don't just disappear into thin air or magically appear out of nowhere. They follow the paths provided by the circuit, and KCL helps us keep track of their movements. So in essence, KCL tells us that electrons don't just disappear or appear out of nowhere. It's like a well-organized traffic system, making sure that every electron is accounted for and follows the rules. And that's the beauty of Kirchhoff's current law. It gives us a simple and effective way to analyze complex electrical circuits. Moving on, let's explore Kirchhoff's voltage law, also known as KVL. At its core, KVL is a principle of energy conservation. It's like a meticulous accountant, ensuring that every bit of voltage that enters a loop in a circuit is accounted for when it leaves the loop. In other words, it's all about balance. Let's break this down a bit. In an electrical circuit, you have something called electromotive forces, often abbreviated as EMF. These are your sources of energy like batteries or generators. Then you have resistors, which are components that resist the flow of current and cause a voltage drop. Now, KVL states that in any closed loop of a circuit, the sum of these electromotive forces and the products of current and resistance is equal to the sum of potential drops in that loop. In layman's terms, the total energy supplied by the EMF is equal to the total energy used up as potential drops across resistors and other components. So let's imagine a simple circuit loop with a battery and a resistor. The battery supplies a certain amount of voltage and the resistor uses up some voltage. According to KVL, the voltage supplied by the battery must be equal to the voltage used up by the resistor. If the battery supplies 10 volts and the resistor uses 5 volts, there must be another component using up the remaining 5 volts. If not, KVL would not be satisfied and our circuit would not be balanced. It's important to note that KVL applies to each and every loop in a circuit, not just the whole circuit. That means that even in complex circuits with multiple loops, each loop must satisfy KVL independently. In essence, KVL is all about maintaining balance in a circuit. It ensures that energy is conserved, that every bit of voltage is accounted for, and that the circuit as a whole remains balanced. So KVL essentially ensures that what goes around in a circuit loop must come back around, both in terms of energy and voltage. Now that we've learned about Kirchhoff's laws, let's talk about why they matter. You see, these laws are not just theoretical concepts that scientists love to ponder upon. They have a practical and critical role in the world of electronics. To put it plainly, Kirchhoff's laws are the fundamental principles that govern the behavior of electrical circuits. They are the traffic rules that electrons follow, dictating how currents flow and voltages distribute across a circuit. Without these laws, we would be unable to predict the behavior of a circuit, rendering us incapable of designing functional electronic devices. Let's delve a little deeper. Kirchhoff's current law, or KCL, ensures the conservation of charge. In essence, it tells us that electrons do not disappear or appear out of thin air. This law allows us to calculate the unknown currents in a circuit, aiding us in the analysis of complex networks. On the other hand, Kirchhoff's voltage law, or KVL, is all about energy conservation. It states that the total energy supplied in a circuit loop should equal the total energy used up. This law is instrumental in determining the unknown voltages in a circuit, allowing for accurate calculations and predictions. Together, KCL and KVL form the cornerstone of circuit analysis. They enable us to understand and interpret the intricacies of electrical circuits, paving the way for technological advancements. Moreover, these laws are not just limited to electrical engineering. They have found applications in various fields such as telecommunications, computer science, and even biomedical engineering. For instance, in biomedical engineering, these laws are used to model the electrical activities of the heart and brain. So whether it's the smartphone in your hand, the laptop on your desk, or the pacemaker in someone's heart, Kirchhoff's laws are at work, silently guiding the flow of electricity, ensuring everything functions as it should. So Kirchhoff's laws aren't just theoretical, they have practical implications in the world of electronics. Let's summarize what we've learned today about Kirchhoff's laws. These two laws, Kirchhoff's current law and Kirchhoff's voltage law, are the cornerstones of circuit analysis. They're like the traffic rules for electrons, making sure everything flows smoothly and predictably. First, we delved into Kirchhoff's current law, or KCL. This law states that the total current entering a junction in a circuit is equal to the total current leaving the junction. Simply put, electrons can't just disappear or appear out of nowhere. This law is crucial when you're trying to figure out how the current splits and combines in complex circuits. Next, we explored Kirchhoff's voltage law, or KVL. This law tells us that in any closed loop of a circuit, the sum of the electromotive forces and the products of current and resistance is equal to the sum of the potential drops. In other words, what goes around in a circuit loop must come back around, both in terms of energy and voltage. This law is key when you're trying to understand how voltage is distributed in a circuit. These two laws are not separate entities, but work together to give us a complete picture of the behavior of electrical circuits. They allow us to track the flow of current and distribution of voltage, providing crucial insights into how a circuit works. In essence, Kirchhoff's laws help us make sense of the complex world of electrical circuits. They are our map and compass, guiding us through the intricate pathways of current and voltage. Without them, we would be lost in a maze of wires and components. So, the next time you're looking at an electrical circuit, remember Kirchhoff's laws. They're the traffic rules that keep everything in order.